No.
9 seconds. He does not go or the ball does not go 112 meters, 112.5 meters in 6 seconds. It goes 9 seconds. That's the total distance, so you do the total time. So this would be 112.5 meters divided by 9 seconds, which is something absolutely spectacular.
12.5.
Units?
Meters per second?
Checking to see what I forgot. That's chapter 3. Any questions? I have one more thing from chapter 3, and then we're going to wrap chapter 3 up. So, any questions up till now? I want to talk about two equations that Hewitt has to at least talk about when you can use them or not. I've sort of talked about it before, but he has a formula, and again, I have the old version of the book. I don't know what page it is on the other one and the newer version. But it's that last section, the free fall section of chapter 3, where he talks, it has a formula, V equals GT. And then I think he writes D is equal to 1/2 GT squared. Well, I'm not fond of using D for distance, but he doesn't have the vector symbol over it. He's not spending a lot of time on that. And the reason he can get away with it, because that V is just a symbol for speed, the reason he can get away with it is this is free fall for an object that is just dropped. So in order to use these equations, there are two really important things. Number one, the initial velocity is 0 meters per second. It has to start at rest. If it's not starting at rest, do not use these equations. The other one is that G is approximately constant. And that's an assumption that we make a great deal. You really can't use these equations if you're in outer space and you let go, and if the moon fell into the earth, how fast would it be going? Well, G is not constant in that case because that's a really huge amount of distance there. But I've seen a lot of students use these equations when V is not 0, and it's just not appropriate. And then another comment is he uses these equations specifically for objects in free fall. You let go and it falls. You can make them slightly more universal if the velocity starts out, initial velocity is 0, so it starts at rest, and then accelerates at a uniform rate. So if acceleration is constant, it's supposed to be an A. Then you can just make it slightly more generalized. I'm gonna put in delta x instead of d. 1/2 AT squared. And so the first problem that I put up on the board with a car or a ball or whatever it was, I had it starting at rest,
Bless
and then
you.
had acceleration at 3 meters per second, a uniform acceleration of 3 meters per second squared for 5 seconds. in essence, we were using these equations here. We could have used this one instead of finding average velocity and then find time. But the reason I did not use this equation is that it is specific to starting at rest.
Is that an A or a 0? Besides F, yeah.
A. I'm hoping they all look like A's now. All right, let's take 5. Stretch your legs. Get some cooked carrots over there and some pineapple. Prefer you not eat it in class, but they're small enough you can eat them during this 5-minute break. I'm gonna pause this. It'd be nice if someone tries to remind me that it's paused. So somewhere on there. Since we finished chapter 3, let's talk about the quiz. Quiz on chapter 3. I'm thinking a week from today. I'm hearing anyone expressing a different opinion?
No.
Other than Latoya? So again, textbook problems. There are certain ones that are assigned that you can find on Blackboard, and I will take one from each type. I think there's 5 different types this time, and I will change the numbers, if there are any numbers.
You're talking about like the plug and chug and think and review and things like
Yes,
that?
yep,
Okay,
And this is on chapter 3?
chapter 3.
okay.
You got more chapter 2 quizzes back here?
No, I had them ready to hand back last week, but you decided not to show up. Because I was asked about that, and I said, oh, I'll have them back next week, and then I kept forgetting that we weren't gonna have class that week, so, yeah, I have them here, and matter of fact, I'm gonna set my alarm, because I've had stuff to hand back to another group for 3 different classes, and I've still forgotten to hand it back to them.
Oh, wow, maybe you should put that in there too.
Yeah, you know, eventually one of them will remind me. All right. So I started the video, I'm pretty sure.
Okay, I was about to ask. I think it is. I see the thing blinking.
And, yep. All right, so we've talked the first chapter about forces and what forces are, how to actually look at a problem and decide what forces are involved. We then have talked about motion, and if I know the acceleration, initial velocity, if I know what's called the initial conditions, I can predict where it's going to be at a future time. And now we combine the two. The relationship between force and acceleration. I might have written it down on the board before, but here it is, the official presentation. What I consider the most important equation in all of physics. Now, there are other equations that become much more practical when doing more complex analyses, but this is at the heart of it. So, F, this is the total force acting on an object. This is mass and this is acceleration. So let's start out with a simple problem. I have a 3 kilogram mass, and I have a 6 Newton force pushing on it. So the A with a vector symbol over it is I'm looking for vector acceleration. How's the velocity changing? The absolute value marks around it means I'm just looking for the magnitude. So I'm not interested in the actual direction, but in this case, the direction is going to be whatever the direction of the 6 Newton force is. Fast, please. So looking at that equation over there, what is the total force acting on the mass?
6 newtons?
Yes. So plugging into that equation over there, I have 6 newtons equals my mass. What is the mass of the object?
3 kilograms?
Times the acceleration. And so the math problem is 6 is equal to 3a. A is equal to
2.
units.
Kilograms. Oh, sorry. Newton. Listen, just go ahead, you know.
I appreciate the faith. All right, there are 2 ways, there are actually 2 different answers that students will give.
Is it? Oh, that's okay. Go ahead.
Go for it, I think you have it. I feel good.
I was gonna stop. No, I'm not.
What would the frizz say?
He got it, he didn't say it.
Yeah, take chances, make mistakes, get messy. All right. So you divide by 3 kilograms, divide by 3 kilograms. And so you get 2 newtons per kilogram. That is a perfectly acceptable answer. Is that what you were gonna say? Should have gone for it. Or, newtons and kilograms are both international standards. What is the standard international or international standard unit for acceleration?
Meters per second squared.
There we go. Or 2, it's supposed to be an equal sign, meters per second squared. Both of them are acceptable answers.
I was thinking that one, 2 meters per second square, but I didn't.
Yeah, it looks like it just sort of comes out of nowhere. But the reason why it does appear here is that the Newton is defined. The Newton, the 3 lines means equal by definition. That the powers that be came down and they said, we are defining a Newton to be this. Is equal to a kilogram times a meter per second squared. So when you divide by the kilogram, you're left with a meter per second squared. But that's the definition of a Newton. It's called a derived unit. So, the simple problem. Now, there's a textbook problem where they did something similar to this, except they did something like a 3 Newton force acting on a 6 kilogram object. And students are so used to dividing the big number by the small number that they get messed up on this one. So that would be 3 is equal to 6 times A. So A would be 0.5 or 1/2 if you're a fraction fan. Meters per second squared.
Did you divide it by 6?
Yes. Or I guess you could answer 3/6 meters per second squared. All right, any questions on this before I make it more complicated? at 3 kilograms. All right,
And this is, you said this is the start of chapter 4?
yes. What is the acceleration? We're gonna do pretty much the exact same thing we did before. The only difference is that the force is a little bit trickier. So I'm gonna plug into F equals ma. So what is the total force acting on this mass?
Is it 10 newtons?
No. I was wondering if someone would say that. It's not, definitely not.
So it's just 6?
Nope, more than that. I will say that you're making this, there's a way, there are plenty of ways of making this far more complicated than it is.
Is it, 6 I hat, minus 4 J hat?
Oh, so close, you're almost there, the only difference is up is positive.
Yes, yeah,
So it's 6 newtons
plus.
I hat plus 4 newtons J hat. I think the example we did before, we had down as positive.
No, it's, yeah.
Okay.
It's the same.
The total force is just that in the I hat direction plus that in the J hat direction. You don't have to get more complicated than that. You can if you want, but you don't have to. And the reason it's not 10 is they're vectors. Vectors don't add that way. You have to take direction into account. So if you want to do magnitude, I have 6 going this way plus 4 newtons going that way. And so the resultant would be the hypotenuse of that triangle. So whatever the square root of 52 is, 16 and 36, yeah, so square root of 52.
Bless you.
What she said. Is equal to 3 kilograms times the acceleration. Now I'm not looking for a magnitude of acceleration, I'm actually looking for the acceleration here. So I'm trying to solve for acceleration, and that is an A, despite what some of you might claim. There we go, a little bit more traditional. Yes?
How did you get 15? Did you do like 4 squared and 6 squared?
4 squared plus 6 squared, I think is 52, unless I. And then the square root of that, it's Pythagorean theorem.
Okay, I was just wondering if that's what you did.
Yes, yes it is.
Alright.
Yeah,
Sorry,
that's
I
right.
misread your eyes then.
That's right.
Okay. Alright. Alright, so we're solving for acceleration, so how do you do it? How do we get acceleration all by itself? By?
3 kilograms.
So on the right-hand side, the 3's cancel out, the kilograms cancel out, and we're left with just A. So my acceleration is, now I got this thing on the left, I got these 2 numbers divided by a single number, and please, show your work. I'm dividing both of them by 3. I'm not dividing just one of them by 3. So I end up with, for this part over here, well actually let's write out the intermediate step, so that's 6 newtons over 3 kilograms I hat, plus 4 newtons over 3 kilograms J hat, or 2 meters per second squared, or newtons per kilogram for those who prefer that, I hat, plus, for fractions, 4/3, for people who don't like them, 1.3 repeating meters per second squared J hat.
So you just did that separately?
Yes, because we're dividing both things by 3.
Because they're going in different directions.
Yes.
Wait, can you explain one more time how you converted from newtons to meters per second squared?
Alright, so Alright, so if I have A times B divided by A, what would that get me?
B?
Yeah, the A's cancel out, and the left is B. Assuming A is not zero for you math purists out there. So, a Newton divided by a kilogram. Well, a Newton by definition, this is, I have no say in this whatsoever. These are the people that somewhere along the lines, the international community, and there's a group that makes this decision, said they defined a Newton to be a kilogram times a meter times, kilogram times a meter per second squared. And then the kilograms cancel out, and I'm left with meters per second squared. It's just because of the way they define a Newton. Is that sufficient, Jency?
Yes.
So now if I asked, what is the magnitude of the acceleration? Well, then we're doing something very similar to that. We're adding vectors, we're finding the resultant. I'm going 2 meters per second to the right, 2 meters per second squared. Up, I'm going 1.3 repeating meters per second squared. And the magnitude is the length of that hypotenuse. And we'll just call this R. R squared is equal to 2 squared plus 1.3 repeating squared, which ends up being something.
2.402?